Okay, this video is about expected value and variance. These are ideas that come from distribution, so make sure you have worked through the previous video. These are mathematical properties of every distribution. Expected value, or mean, is a measure of the center of the distribution. It has a lot in common with the average. There are two commonly used symbols for it, E of x and the Greek letter mu. They are generally interchangeable, and it depends on the author's preference. You've probably heard of other measures of the center of the distribution like the median and mode, but we're not going to worry about them. Variance is a measure of the spread of the distribution, so it tells you something about the likely distance between numbers. There are two commonly used symbols for it, V of x and the Greek letter sigma squared. We'll start with the expected value. It has a fairly simple formula. You multiply each possible outcome, x, by its probability, and then add it all up. The more savvy students might recognize this as a weighted average, where the probabilities are the weights. But this isn't necessary to appreciate the calculation. Let's apply this to the distributions from the last video, starting with the distribution of one die roll. Here is the distribution, and here is the calculation of the expected value. And it all adds up to 3.5. This makes good sense because all of the outcomes are equally likely. Therefore, this center of the distribution should be right in the middle, which is right at 3.5. Now let's apply the expected value to the distribution of 3 coin flips. Here is the distribution once again, and here is the calculation of the expected value. And it all adds up to 1.5. This also makes good sense because this distribution is symmetric. So the probabilities on the left side and the right side are mirror images of each other. So these centers should again be right in the middle, or 1.5. And finally, here is the last example from the previous video, the distribution of the number of yellow balls drawn from a jar. Let's apply the expected value calculation. And it all adds up to 0.8. You may have noticed so far that none of my expected values were whole numbers, but each distribution that we used was only defined for whole numbers, so that may seem like a contradiction. But the expected value doesn't necessarily have to be one of the possible outcomes. It's much better to think of the expected value as a long-run average. So if you did the green and yellow ball game 10 times, then you would expect to get a total of 8 yellow balls, which is an average of 0.8. Naturally, there is still luck involved, so you probably won't get exactly 8 balls, but there's a high probability of that. It'll be near 8. So the average number of yellow balls will be near 0.8. And as you increase the number of times you play the game, you increase the probability that the average converges to the expected value. If that sounds a lot like the law of large numbers, then you have been paying good attention. Just remember that expected value only makes sense in the long run. In the short term, random experiments are more influenced by luck than anything else. Okay, let's move on to variance. You need to calculate the expected value before you start because it's used in the formula. I'm going to use the Greek letter mu since it's a little more convenient. Here's the formula. For each possible outcome, you subtract the expected value, and then you square the result. Then you take your answer and multiply it by the probability of that outcome, and then you add all of them up. So it's a much longer calculation. All right, let's go back to our example and find the variance of one die roll. We already found the expected value earlier, and it's equal to 3.5. The variance is a longer calculation, but here it is. There are 6 terms, one for each possible outcome, and in each one we subtract 3.5, square it, and then multiply it by its probability. And it all adds up to 35 out of 12. There's a shortcut version of the variance formula, and it looks like this. It's the expected value of x squared minus the square of the mean. And here is how you calculate the expected value of x squared. It's almost identical to the expected value, except that you square each possible outcome. Let's use the shortcut formula to find the variance of 3 coin flips. We already found the expected value earlier, and it was equal to 1.5. Let's find the expected value of x squared. Here is the calculation. And it all adds up to 3. Next, we take this result and subtract the square of the mean, or 1.5. And that gives us our variance equal to 0.75. That's a lot easier than plowing through the other variance formula. Standard deviation is defined as the square root of the variance. This is the measure of spread most commonly used in practice. Variance is useful in statistical theory, but standard deviation is practical for real-world understanding. It's a lot like the expected distance between the possible outcomes and the mean. And it's measured in the same units as the outcome, so it's a very natural way to measure the spread of a distribution. Okay, you now have 3 problems to work on. Good luck with that, and I'll see you in class.